Hey guys, so in this video I figured I would split this up into three separate parts, so if you need to fast forward based on what you want. The first one is just getting an overview of when we have sprockets connected, bicycle situation, things like that, what the relationships are. The second part will be going through a bike situation that will give you the pedals and RPMs, and we have to find our linear velocity. And then we're working backwards when we were giving you the linear velocity, how fast we're actually pedaling. So I made this in GeoGebra here to represent a pedal situation. This small circle here that has a radius of 1 is my pedal, and then this rear sprocket, this rear gear, has a radius of 2. So right off the bat we should know that there's a transmission factor since they're varying sizes. Again, that transmission factor I can take driver divided by follower. So a radius of 1 divided by a radius of 2. This one should spin half as fast, the big circle here. And remember we said bigger circles go slower, smaller circles go faster. Now what I have here is a little animation to see that. So as you can see, as time increases, just watch, oops, sorry, how many times that C goes around. That's once around, 2 times around. So once I hit that 2 times around, then that back tire went a full revolution. So it's going half as fast here. So again, maybe I'll just turn the animation actually on now and you can watch it. So again, there's 1 turn for the little, 2 turns for the little, 1 for the big back wheel. But then I've also added this radius to what's the rear sprocket, and then this dash line would be, for example, the rear wheel. But you notice that they share the same angular velocity, and I think that's just something we got to know about the situation. Some of us need that to sink in a little more, that that radius AD there going around the rear sprocket has the same angular velocity as that radius AI there. So that point I is traveling the same RPMs as point D is. So that's a big deal in the bike situation, because once we find the rear sprocket, we can find linear velocities of wheels because we know their angular velocities. So I'll stop that, and then we'll go through our bike situation here, which I've created, and just tried to find some images that show our situation, that I have now a bigger pedal and a smaller rear sprocket. We'll say the pedal has a radius of 8, rear sprocket has a radius of 3, so there is a transmission factor other than 1, and then the radius of the tire is 30 centimeters. So we'll just walk through these calculations, and I put some helpful ones that are given as we are pedaling at 90 RPMs. So I know the angular velocity of the rear sprocket is going to be the transmission factor, when this, in this case, is 8/3, times the angular velocity of the pedal, which is 90. So eventually that rear sprocket is 240 RPMs. Now this is the relationship we saw in GeoGebra, that the rear sprocket is spinning just as fast as the wheel is, or vice versa. The wheel is spinning as fast as the sprocket, I guess. So now I know the wheel is going 240 RPMs also. Our linear velocity equation then is just circumference times angular velocity. Now just be careful of what you're finding the circumference of, what you're taking the angular velocity of. If we want a linear velocity of the bike, we need to know what's touching the ground and actually making us move, which is the wheel. So I need the linear velocity of the wheel, the circumference of the wheel, and the angular velocity of the wheel. But I have those now. So the linear velocity of this wheel is the circumference of the wheel, which is 60 pi, times the angular velocity of the wheel, which is 240 revolutions per minute. Units are always good in this, so I should put that this is centimeters. So I know then once I go through this calculation, it will be centimeters per minute. So I'm going to take that 240, this times 60. I'm going to leave the pi out for a second here, which will be 1,000 or 14,400 pi centimeters per minute, which is a legitimate answer, but it's not very useful for us to actually know a speed. So we've been doing a lot of calculations to get 2 kilometers per hour. I'll just do that quickly. We have 60 minutes in 1 hour. We have 100,000 centimeters for that 1 kilometer. So I have my minutes cancel. I have my centimeters cancel. I'll be left with kilometers per hour. So I'm going to take that 1400, keep calling that 1400, sorry, 14,400 times 60 and divide by 100,000. And if you can keep it in exact form, we should. And MathFrac is always a nice one in here. I can make that 364 over 1,000, but it looks like it may be a nice, not too bad of a fraction here, 216 over 25. And of course, we have that pi still involved. So I'm going to do that answer in my calculator just to get a rough estimate of what that is in decimals times pi. And there it is. So our linear velocity equals 27.14 kilometers per hour, which is a reasonable speed for a bike, so that makes sense. So now we're going to go through where I actually have to work backwards. If I'm given this linear velocity, can I work back to find the pedaling? But again, you're just working backwards through these calculations. So let's say we are going, let's go a little bit slower even. Let's go 20 kilometers per hour. That's my linear velocity, which is going to equal the circumference of the wheel again, times angular velocity of the wheel. My preference, I guess, is to convert it first, but you don't have to. Since I know the circumference is going to be in centimeters, I'd rather have this in centimeters. So I'm going to divide by 60 minutes this time. So I want my 1 hour to cancel out. And it's really just the, we did times 60 over 100,000, so now we're doing 100,000 over that 60. So this is centimeters and kilometer. So I'll get that in my calculator. I'll go 20 times 100,000 divided by 60. And I get that 33,300 and so on and so forth. And you can keep that as a fraction also. I'll go to decimal just to save time here. 33. And again, and now that's in centimeters per minute. My hours canceled, my kilometers canceled, which equals the circumference of the wheel, which was 60 pi centimeters. And then I'm going to find the angular velocity of the wheel. So just one multiplication here. All I'm doing is dividing by 60 pi. You just have to be careful with that in your calculator. Divide by, in parentheses, 60 pi. And if you wanted to be exact, you just divide by 60 and then MathFrac it and keep the pi in the denominator. So in this case, the angular velocity of the wheel then is 176.84. And this is where we would probably want to stay exact just because I am rounding that now. But I have the relationship from before with the transmission factor that I know the angular velocity is the same as the angular velocity of the rear sprocket. We saw that in GeoGebra 2. So thus I know if I take 8/3 of the angular velocity of the pedal, that's going to equal the angular velocity of the rear sprocket. And now we know that. It's right here. So if I take that answer and divide by 8/3, which is the same as multiplying by 3/8, it'll give me the angular velocity of the pedal. I'm going to take that times 3/8. And I get 66.31 revolutions per minute. And that's the angular velocity of the pedal. So before we were pedaling 90 RPMs, I believe, and we were going about 27 kilometers per hour. We went a little bit slower. We said 20 kilometers per hour. Now we're pedaling a little bit slower, and it should all be, almost, I don't know if I should call it proportional, but essentially it is. We only have constants of pi and circumference and things like that that are changing. So hopefully this helps out. You know, all three ways we want to understand all the angular velocities that are related when the wheels are connected, or if we're just talking about points on one wheel there. So I hope this helps. Have a good one.